Okay, welcome back. So I think that during the break I realized that I didn't really introduce myself because we were trying to get things going. So my name is Kevin. I work for our studio, and I actually spend most of my time working on the Sparkly R package. So does anyone here ever use Sparkly R? Okay. Yeah. All right. But I try to play around with some of our the deep learning ecosystem in R, and that's sort of why I'm here. So for this second half, I actually have more content than I realized. So we're gonna take a quick poll because just in case we don't have enough time to go through everything. So what I have here are I have a text classification example, and then I have a time series forecasting example using, and both of these are going to be using, I believe, recurrent neural nets. And then also an example just doing predictive modeling on some traditional structured data. So I wanted to see, like, I want to cater to you guys. So who wants to do the time series stuff? Okay, so that's definitely over half the room. Who really wants to do like text classification? Okay, a little less. What about like structured data? Good old tables. Yeah, one. Okay. Okay. I was totally expecting that there's going to be more interest for the structured data, because that's what that's the easiest way to go from current technique to deep learning and then writing a new paper on it. But that's okay. So let's do let's start with the time series, and then see how we do there. So this is going to be the fourth notebook. Is called Sunspots RMD. And then okay, so let's do that. So this is a time series data set. To be honest, I don't know exactly what these are, sunspots. Who knows what sunspots are? Who has seen this data set before? This is a built-in data set. All right. Do you know what they are?
So I think it's like in astronomy, like the sun, it just has like brighter spots and spots that are not so bright, and you can measure these. And I think there's measurements going like 300 years back.
Okay. All right. So sunspots, according to this gentleman, is basically on the sun, you have some spots that are bright and some spots that aren't so bright, and this is basically quantifying them, and then you have some historical measure. Okay. So is that accurate? So you have some historical measure of like how many bright spots there are over time?
Yeah, I think it's the dark spots.
Oh, the dark spots. Okay.
I think the sun goes through cycles, but the cycle is not always the same length.
Got it. Okay, so this is our data sets. All right, so he wasn't kidding when he said like we got hundreds of years of observations, and these are monthly observations. And then, I guess the way we interpret this is like how many dark spots the sun has, and then we're gonna try to find some patterns. And we can visualize this a little bit.
Should that be Tibble?
It should be Tibble, and it should have already been installed. So apologies for that. And do not install from Crane, because I think the Crane one has a bug unless she patched it in the past day or so. So we are going to find out how to install this from GitHub. All right. Yeah, but I don't want Tibble. I want Sybil. Yeah, all right. Okay. All right. I think this is a line. Tidyverts. I think we're really stressing the conference Wi-Fi here. That's fine. I think. Oh, yeah. All right. All right. So this is what you're going to install from GitHub, tidyverts/Tibble, T-S-I-B-B-L-E. Is Tibble for time series, hence the TS, yeah? And this function here, it basically takes a time series object and then converts it to a data frame so we can run ggplot on it.
Did you show that package installation?
Oh yeah, sorry. Are we good? Anyone have issues installing this package? I see people shaking their heads. Is that?
Still installing.
Okay. And don't go to where I'm going right now. This is something else. Okay, are we good? Who's not? You got it. Who doesn't have the package installed? Okay, and everyone can run this this block right here. Okay. All right. So this is the time series that we're gonna try to work with, and we're not gonna worry about stationarity and any of that. We're just gonna throw some deep learning techniques at it and see how we do. So the goal is going to be building a model that's going to take like past 10 years of data and then predict the next 10 years. So this is a pretty long horizon, but let's just see what we can do with it. So this is going to be going 120 time steps into the future. So there's a bunch of different ways you can do time series forecasting with neural networks. And I think this will be an appropriate time to, and this will be quick, to do what we did before, and then use some slides that other people have put together. Full credit goes to them. And by the way, at the end of the session, I have a slide with a bunch of resources and online courses you can go to. So you can, for example, like this lecture here is like an hour if you want to check it out. They have YouTube videos, slides, and then this is just one of many different classes that have been open sourced. So we're going to talk about recurrent neural nets, and it's basically just like a feed-forward neural net that we work with in the beginning of the session. The only difference really intuitively is that instead of feeding in your inputs all at once, you're going to be feeding in the inputs sequentially. And then there's some state that's sort of maintained as you as we go on in the different time steps. So in this case, the x's are the inputs, and the h's, and then I think the formulas are up here. So this is a vanilla recurrent neural net. Don't worry too much about the maths, but you can definitely dig into it. But the intuition is that we're feeding in these inputs sequentially, so your neural network is learning something about the temporal structure of your data. And I think that's okay for now. So basically, our vanilla feed-forward neural nets, you know what they look like. You have different layers, and then they're fully connected from the inputs to each subsequent layer. And then for the convolutions, we took the filter, and then we slid it across our images. And then for the recurrent stuff, we impose some sort of temporal structure to them, so they can learn from sequential data. So this will be like time series data, or things like natural languages where there's some sort of order that's involved. So going back to this picture, so there are different ways you can set up these recurrent neural networks. So on the left here, we have the many to one structure. So basically, you have a bunch of inputs that are fed in sequentially, and then you have an output that comes out. Okay, and then we have two types of many to many. The one on the right, so this one is a little more straightforward. It's just like the many to one, except at each time step, your neural net is going to give you an output in addition to passing the state to the next time step. Okay, and then for the many to many case, we're feeding in the inputs again sequentially, and then instead of having the first time steps outputs any predictions, we have this the state that's maintained go on in time and then produce the outputs. So this might sound a little abstract, but it's going to be more concrete, I think, as we go through some examples. So the first way we're going to attack this problem is to use this many-to-one architecture on the left, and then we're going to produce predictions one step at a time. So let's do that. And before we do that, we have to do quite a bit of data pre-processing. So let's go through what this is doing. let's hope all the packages have been installed. All right. Okay, so this is slightly tricky. So this make series helper function, what it's going to do is it's going to take a time series, and then it's going to return a list, and I wonder if we can pull out one of these to just illustrate what that looks like. So we have our data frame right here, and then data look back. Okay, so okay, so if you think about it, at any point in time, you have some values that are sort of behind you that have already happened, and then some values ahead of you that hasn't yet happened. So what we're doing here is all right, so sorry about that. So basically what we're doing is we're computing for each step in time, we're computing a look back vector of the stuff that's immediately that happened immediately prior to our targets. And then we also have, so don't worry about target lag for now. But basically at each point in time, we have stuff that's happened and then the stuff we're trying to predict. So going back to our, our goal is we want to be able to feed it 10 years of this measurement and then try to predict the next 10 years. And then I'm going to attempt to walk through this for a little bit, and then if I fail, we can move on. Okay, so all right, so basically this column argument that we pass to make series, it's the scaled value of the sunspots data. So let's talk about the scale value first. So I think that's going to get our heads straight. So we're going to define this this function that is going to return a couple functions. All right. And what it's doing is the base, our scale function is basically going to scale your data, calculating the mean, subtracting the mean, and dividing by the variance. And then using the output of scale, we can define a function that does the scaling, and then another function that inverts that process. So this function actually is a factory that's going to return a couple functions. So here we are using the first few hundred years of our time series. And when you're doing scaling, you want to learn your scaling values on your training data. You don't want to learn your scaling values on your entire data set, because that's sort of cheating and looking into the future. And then that's what we're doing here. So then we're just using the, we're subsetting, so window is going to subset this time series from 1749 to December of 1992. Again, that's our training range. And then we're going to get, make scalar will return a list of two functions, the scalar list, which is going to scale, and then the descalar function, which is going to multiply by the scale value that's returned by the scale function, and then add back the center value. Does this piece make sense? Yes? Okay. So then we take this time series, and as Sybil is going to turn that into a data frame with an index and a value, and then after that, we're going to assign a key to each of these observations based on if it was in the training range, the validation range, or the testing range. Are we familiar with the concept of train, validation, and test? Who wants me to just go over that? Okay, so when you're building a model, there's a bunch of things you can tune, right? So in neural nets, you can decide like how many layers you want, what type of layers you want. So the wrong thing to do is to take all of your data, build your model on all of that data, and then test it on all of that data, because then like in real life, you don't get to see the future. So when you're during your model building process, you should try to simulate that, and then in time series, usually what you do is you have temporal cuts of the data, and the reason why we have like 3 different subsets instead of just a train and a test is that when you're doing hyperparameter tuning, you're going to be using the validation set over and over. And then if you use it a lot, you're going to be overfitting to your validation set. That's why you should always have a testing set that's you sort of put in a drawer, and then you don't look at it until your project is done, and then you take your model and then predict on the test set, and then those are the numbers that you're supposed to report in your paper and to your client, but sometimes that doesn't happen, but that's what you're supposed to do. Anyway, so that's why we have this process right here. And then so then we add a column that's called scale value, and then that's really just scale value. We're passing value to scale value, and then recall that scale value is the function that came out of this make scalar function factory. And then here what we're doing is we're making these look back and targets time series, basically subsets of the time series of these scale values. And then this piece right here is super confusing. It's confusing enough, okay, because I can't even figure out what I did. All right, so seek along column. So this function basically, you have. I can't spell. All right, so basically when the column that we pass to it is the scale value, right? So then it's basically giving us a vector of numbers. So it's basically 1 until the very end. And then we're applying a function to each of these indices. And then what we're doing is we're defining the starting point and then the ending point of where we want to do the subset. So here, this is our scale value, and then we're defining the start and end here, and then what we're doing here, so time step should be 120 because that's the window that we care about, and then we're saying make the series so that it ends at 1 step prior. Okay, and then for the target, what we're doing is we're saying, okay, we want to make a time series out of this scale value column, and then we want to start at 0, which is now, and then we want to go until time steps -1. And then that's going to give us that's going to give us 120 values. So doing some hand waving here, but are we mostly convinced that this is what it's doing? And then if you have a more clear way to do this, definitely send a pull request. All right, so we have our data. We got at each point in time we have some look back series, and then we have a target series, and then we'll talk about the target lag in a little bit. The target lag is basically the target lagged by 1 time step. Okay. So I did mention that a lot of the work in doing these deep learning stuff is manipulating the data. So what we're doing here is we're going to define this function make Keras data. We're going to pass to it a data frame, specifically the data frame that we just created. And we're going to compute our x's and y's. So for the x, we're going to take the look back stuff. So, excuse me. So remember that a look back is a list column. So it looks something like this. So each element in look back is basically 120 values. And then remember that we need to reshape our data so that the first dimension always corresponds to samples. Okay, and then for time series, the second dimension will be the time steps. And then the last dimension here will be how many different variables you'll have. So this is a univariate time series, so this will be 1. If you were doing multivariate forecasting with a multivariate time series, this will be the number of variables you have. Okay, so this is samples, and this is time steps, and this is 1. And again, this was 120, which we defined earlier. So for y sequence, we have, let's go to y first. I think this should make it a little clearer. So y would just be a scalar for each sample, and then y sequence is going to be the whole target sequence. So in this case, we're just taking the first value of each of the the forward-looking sequence is in Y sequence. So again, Y sequence, we're taking the target, and then we're manipulating it with the same way we did with the X. And then the Y sequence lag is just the Y sequence lag by one time step. And then make Keras data is going to return a list. The X, so I thinking about the timeline, we have the X is what happened before, and then the Y is just one value, and then the Y sequence is 120 values starting from now. Is that part okay? Okay, and then for our training data, we're going to filter it so that we only look at the stuff after 1758. And that is because if you think about it, if you try to get 120 prior values, monthly values, if you're only like 2 years in, you're gonna get 24, and then you can't get any more. So this is this number is special because that represents we want to start our data sets. The first target should be 10 years from the beginning of time in our data set, so that you can have your predictor variable that goes back 120 time steps. And then the validation is just a validation. And then we also have the full training data. So going back to our train validation and test, you build your model with the training set and the validation set. And then at the end, you can test your model on the test set. But before you do that, you should train the model with the specific hyperparameters on both the training set and the validation set, right? And then once that's done, and then you're going to deploy this, for production, and then start predicting stuff after today, then you can run your model on everything that you have. So we won't go through this whole process for every one of these examples, but this is like sort of the standard way to do things. So we implement it here, and then the prediction data here. So this is so this number would be. Let me see if I can justify that number. Okay, so our testing range is from 2003 to 2012. So our prediction data should be the X, right? The X in our prediction data should be 120 time steps just prior to the first number that's in our test, right? So that would be this specific row. So prediction data is simply one row from that data frame we created, and then the X here is the 120 values prior to January of 2003, and then the Y sequence will be 10 years of data starting from 2003. Okay, any questions about this setup so far? Because this is pretty crucial. right, so who's like, I don't know what the hell you're talking about? And who's like, okay, I'm pretty sure I know what you're doing. And that guy's like, oh, I can't take this anymore. All right, so we're gonna plow through. All right, so we have our training data. We have a list of x values. So x here. Again, we check the dimensions. We have these are our samples, and then this is the time steps as promised, and then 1 is because we have a univariate time series, and then the y is just like one value, okay? So this is the value immediately after the x. And then the y sequence is the y and then all the stuff that goes after it. So the reason why we have the y and the y sequence is we're going to attack this problem using a few different approaches. And then recall that in our first attempt, we're just going to predict this y and not this y sequence in our model. So let's define our model. So again, we're going to use the sequential API, and then we're going to add an LSTM layer. So when you're working with recurrent neural networks, you usually use either the LSTM or the GRU. So LSTM stands for long short-term memory, and then GRU stands for gated recurrent unit. So these are sort of the standard recurrent network units that you use when you when you're working with sequential data. So here we have the number of units, and then you can again think of this as like how complex you want your network to be. And then the input shape in this case. So when you specify an input shape, the first dimension is always omitted because it's always the samples. So you don't even have to specify that. And then again, this will be the second dimension. So that's the time steps, and then this will be the number of variables you have. And then at the end, we hook this up to a fully connected output that's with 1 unit. Okay, so then in this case, we're working with a regression problem, so we can use mean square as our loss. Are we good? All right. So now let's fit this thing, and then instead of adding a validation split argument with remember we had like a 0.2 in the previous example. Yes, question. Got it. So question was, how do we decide 128? Is it related to is it related to, say, how long your input sequence is and other things? Not really. So this could be basically, it could be anything you want. And you usually start with some number, and then you see how you do in validation. And then if you, and actually even before that, if you can't overfit to your training set, then you want to make your network more complex by either adding more units or adding more layers. So it's an iterative process, and then this is just like an initial value, right? So then, and there's really, I don't think any good guidelines for that. So I could easily have put, something else here. Anyone else have different experiences?
It's just a hyperparameter. You just needed to try lots of numbers.
Yeah, yeah. It's like when you're doing column sampling in gradient boosted trees. It's like, oh, should I do 0.8? Like, why? How can you justify that 0.8? It is what it is, and we'll see how we do.
The higher the number, the more computationally intensive the
Yes. Yeah, the higher number, the longer it's going to take. The more layers you have, the longer it's going to take. All right, so let's try to run this thing. So again, we have the validation data where we explicitly specify what validation data we want to use, and that's because in this case we have a temporal structure to our data, so it wouldn't make too much sense to just randomly sample. It's probably okay in most cases, but in this case we chose to respect that temporal component. All right, so when you're looking at these things, if your training loss is not going down, you have a problem. So if your training loss is not going down, it could be a few things. Maybe the data pre-processing was screwed up, so double check that. Or maybe your network is just too small to be able to detect the patterns that you have in your data. So the typical workflow is you first want to get your training loss to go down, and then it should keep going down as you train for more epochs. And then your validation loss should also be going down to a certain point, and then you should expect that you've overfitted to the training data, so then your validation loss goes up. So before that happens, you should make your network bigger and bigger until you can get the training loss to go down. And then when you start overfitting, you can start thinking about regularization techniques. All right, so now let's say we iterated on this, and then we decided on how many layers we have. Let's say this is the perfect model that we want. What you would do is the way to reset the weights on your neural network is really just to redefine your model. So that's why we basically copy pasted the code from before and then recompile. And just calling compile is not going to reset the weights. So keep that in mind. So here we're going to fit this model on our full training data. So that's both the train and the validation. And then sometimes the the number of epochs is also a hyperparameter that you can tune. You can, for example, look at this plot and then see like when the validation loss starts going up, and then maybe you can use that number as the number of epochs to train. And this is not an exact science, right? You know, it's once you have more data, you don't know like ground truth, like how that's going to behave. But these are just some heuristics you can try. Okay. So recall that this model is going to output basically one number. And in our problem statements, we wanted to be able to look 10 years into the future. So how do we deal with that? And anyone here work with like time series forecasting problems? What's one way that you handle this? If your algorithm only spits out like one time step into the future. Okay, so suggestion is use the prediction as the next value, and that's exactly what we're going to do. So we have this little helper function here, and let's see if I can decode this. Okay, so this function forecasts future values. It's going to take a model. It's going to take some x, and then it's going to take some steps argument. So we're going to initialize this forecasted numeric vector. And then for each step, so what this function does is it's going to give you, this vector from 1 to 120, because we're going to pass 120 to 2 steps. And then we're going to take x, prediction, specifically prediction data x, and remember this was the 10 years just before January of 2003. So we're going to reshape that into something that can be fed into the model. So in this case, our samples is just 1 because we just have, one sequence. It's still got 120 time steps and it's still univariate. And then we're going to call the predict function on the model and our x. And this should give us just one number. So forecasted, in the first step, we're going to concatenate this prediction in there, and then we're going to update our x by removing the first value of x, because that was the oldest value. And then we're going to concatenate the thing that we just predicted. So as we predict one step forward, we're going to drop our oldest value and then add this new value as our x. And then recall that all of these values were scaled because we called the scale function on it. So we need to call descale value, which is going to multiply by your variance and then add back the mean that was subtracted. So now we have predictions, and then we can check that it's got 120 20 values. So we're going to try to visualize this by using a helper function called plot predictions. So what this is doing is taking the data. Remember, data is the name that we give to our data frame with all the engineered features. And then we're just going to look at testing. And then what we're going to do is we're going to add a new prediction column that's the predictions that we just computed. And then we're going to take this data frame and then R-bind it with some stuff that came before, basically to see that to see how what sort of patterns the model try to capture. And then this is just some standard tidy stuff to try to get this into ggplot. Let's see if I can pull this up. All right. So the red line here, can we see this okay? I guess you can see on your screen. So the red line here is what we predicted using that iterative process. And then the green line is the actual values. So we see that this is what this is doing. So any questions on this first approach? And then I feel like that the hardest part was like just massaging the data. And as you work on your problems, you'll see that pattern too, where massaging the data is a lot of the work. Question here.
Yeah, I wonder whether we have some sort of comparison with the classical methods for time series forecasting, like AR and A things, to see whether we've been able to improve, at least in mean square error or in some other measure with respect to classical methods.
Oh, so was the question whether we can compare this or whether we have compared this to classic algorithms? I have not myself. I have heard anecdotally that your classic time series algorithms like Garch or Riemann and all that, they're probably better than some of the deep learning stuff in most cases. And then if you want the deep learning stuff to do as well as those, you will have to spend a bit of time, tweaking the architecture. But I actually haven't seen like systematic studies on this. So maybe that's an idea for a new paper. Yeah. But one of the things that I think deep learning approaches can take into account is that they can look at not just the time series data. They can also look at other descriptive variables. So if you have another data set that are more like, I don't know, like more qualitative, or and then have different features that you think could be relevant to doing the forecasting, then I think like the classical techniques won't be able to take those into account as easily. So let's say you were making this up now. Let's say you were trying to forecast like power consumption, right? So maybe you want to look at the weather, the traffic, and whatnot. And then because neural nets are really flexible, you're able to sort of take all of those into account, feed it into the model to produce the predictions. Whereas if you're using classical time series techniques, you're sort of just stuck with the time series data.
My understanding was that the arena models do allow for incorporating explanatory variables beyond just historical time trends.
Okay. Yeah, the comment was that arena models may be able to also take into account these other variables. But I'm not too familiar with that. Yes, question.
So is one of Brand's prediction ones the same as yours, or are we looking at Brand prediction ones?
Could you repeat that a little louder?
Sorry, with the red prediction one, are we meant to have the same pattern as you? Is it meant to be exactly the same shape?
Oh, no. All right. So great question. So the question was the red line that you see on your screen, is it going to match mine? And the answer is no, because we initialized, the weights are randomly initialized. So every time you sort of fit your model, you're going to end up with something different. So that's a feature, not a bug. Yes. Yeah, and then to follow up to that question is like, oh, I'm working at a bank. I'm doing like stress testing or what I'm doing forecast. I can have, a different result every time. Like my auditor is gonna, kill me, blah blah blah. So it's just like random forest and like stochastic GBM. You can have different values, but if you were to ensemble more of these models, then you're gonna get a result that's more stable, and then you can make it stable enough for whatever use case you're doing. But that's totally legitimate. Yes.
I know in some image processing applications of neural networks, people have done like this big convolution stuff, so they can actually visualize a general meaning of different layers. And this layer with this swirl, this layer with this line. Is there anything in other applications, but specifically time series, that you could look at a set of weights and say, oh, this is something cyclical, or this is a trend?
That great question. So the question was first a comments where for convolutional networks where you can look at these things like activation maps to see what sort of features would trigger specific activation values, and as a way to sort of interpret what the network is doing. And then the question is there something that we can do with the recurrent neural networks as applied to time series data? And I don't know the answer to that. And but I do know that there's a lot of current research on getting more interpretability out of these algorithms. So this is along the same theme with if regulators wanted to look at my model and then see what it's doing, that there should be some way to sort of explain the results, right? But there are also applications where you don't care at all how to explain the results as long as you get good predictions. But that's definitely a good question. I think a lot of people care about that. Okay, anything else before we go on? All right, so let's go to the second way. So this time around, what we're gonna do is instead of putting a 1 there in our output, we're going to have the model output like 120 time steps. That's the only change. And this line here doesn't really do anything. It's just to help us make sure that the output of the model is going to match the y values that we feed it. So let's take a look at this. And again, going back to the where did that go? This is still the many to one case. We're still using the output from the last time step, except now this blue box here now is a vector of 120 values. So let's go back now. So we define the model. And then now we need to tweak our training data a little bit. So okay, so the justification, if you see that we in the filters here, we have something like this. We're taking when we're building our training data, we want our year of observation to be less than the minimum of the validation range. So recall that validation range is from 93 to 02, and then we're subtracting 10 from that. And then this is because, if you recall, our y value is just that scalar, but then our y sequence is going 10 years into the future. So then we have to make sure that when we're feeding in our training data, we're not looking past, we're not looking into anything in the validation range, and we're just looking at stuff in the training range. Does that make sense? Does that make sense? Okay. And then similarly for the validation and the full training data. Okay, so we're gonna skip the tuning of the stuff in the interest of time. We've done that already. And then let's say that we've decided on where our model should be. And then this time we're going to feed the Y sequence instead of the Y as our output that we're trying to learn. So we're going to fit this and then get some predictions out of it, and then plot the predictions. And I actually also mentioned that this is not like the only way to validate time series models. You can also, at each point in time, you can train a model on the values prior and then test it on the values that come after it. But that would require training a lot more models. So this is the approach that we have taken. All right. So this is what that would look like. Yours probably looks a little different. And again, we're sort of looking at these things qualitatively. We're not looking at any absolute quantitative measures because we're not spending a lot of time tuning these networks. But this is just to illustrate the different ways you can do this. So questions on this second approach? Okay, so for the third approach, we're going to do something that's closer to this picture on the right. So practically, the only thing that's different is we're going to pass return sequences is true to our LSTM layer. And then that basically allows us to get an output at each time step. So the number of outputs that you get with this depends on the number of time steps in your input. So if you put in 120, you're going to get 120 back. Just remember that many-to-many picture. And if you put like 240, you're going to get 240. So let's do this. And then we're calling this the time distributed way, because there's a time distributed function in Keras that sort of gives you a it would put a dense layer on each of the time steps, which is what we're doing right now. So it's that function will be redundant, but in this case. But if you ever see a time distributed function used in Keras, that's what it's doing. So in this case, our predictions look something like this. And then return sequences can also be used when you want to stack recurrent layers. So if we, so let's make this a little smaller and then do something like, I think I missed a pipe. Okay. So if you ever wanted to stack recurrent layers, you have to use return sequences, because these recurrent layers, they require you to have as inputs that many time steps. And then if you don't have return sequences, then this layer LSTM is going to just give you one number that corresponds to the last time step. So this is the way to stack recurrent layers, and you can have as many as you want. So let's let it run for a little bit. All right, so that's what the predictions look like. Okay. So this last one is going to be a little more complex. So this one will correspond to this many-to-many picture right here. And this approach is sort of inspired by machine translation. So in that specific application, you could have like a French sentence that you feed into the neural net, and then it would output an English sentence that's supposed to be the translation from here. So it wouldn't make sense in this picture on the right, because you don't get to see the entire sentence before you try to translate it. And similarly, in time series forecasting, if you went back to the example we just did, and then you messed with the values that were close to the present, it's not going to affect your first few predictions. So you could argue that that would be a drawback to the time distributed approach that we just did. So this last approach that we're going to go through is there's just a couple names for it. One's sequence to sequence, and the other one is encoder decoder. So I'm gonna read this. I think this is pretty concise. So we have a couple different networks. So one is the encoder network that's going to summarize the data, the historical data, and then it's going to summarize it and then basically put it into like some. It's going to give you some numbers, but these numbers are not directly interpretable. But then you also have a decoder network, a separate network that's going to translate this summary into your forecast, which you can then interpret. So each step in the prediction depends on the output and the hidden state of the previous time step, and then so during training we provide the actual lagged values, and during prediction we feed back the prediction for the previous time step into the network. So I think if we go through this, it's going to make a lot more sense. So first we specify the dimension of the layer. You know, this is a hyperparameter that you have to tune. So let's just say 128 for now. And then what these next few lines do is we first create an input layer, and then we're going to use the functional API as opposed to the sequential API, because this model is more complex. So we have an input layer that we're going to call encoder inputs, and then this is a shape. Again, it's the same as before. You know, we got 120, and then it's univariate, so we have a 1 at the end. And then we're going to encode these inputs using an LSTM. And then we're going to call that encoder results. And I think it's worthwhile to just run these things so we can look at them. So encoder inputs is a tensor. And then encoder results is going to be a list of tensors. So this is the output, and then these are going to be your hidden states. So the LSTM has a couple of hidden states, and again the details are beyond the scope right now, but let's just roll with it. So we're going to call the hidden states that come out of this as encoder states. And then what we'll do next is so this takes the value prior to the value being forecasted, and then feeds it to an LSTM with hidden state initialized using the encoder state. So the decoder inputs. Let's see what we're doing here. So we have we have an input layer, and then when we say null, we mean that we mean that we can take an arbitrary number of time steps. So this is the implementation detail that let's not worry about this for now, and then we are going to define an LSTM decoder LSTM layer. So this is going to take whatever inputs you have, and then we're going to initialize this decoder LSTM layer with the encoder hidden states that that we summarized from the encoder input. Okay, so then once we have that, we have the a dense layer that's going to take the outputs from your decoder results. So that was this right here. And then return basically one number. Okay? So all of this is definitely somewhat confusing. So then in our first model here, our inputs are going to be our encoder inputs and the decoder inputs, and then I think it will make more sense to look at what we actually feed these things. So we're going to feed to the model the full training data X. So remember these are the lookbacks. So then this will correspond to the encoder inputs, and then the decoder inputs will be the lag values. So this Y sequence lag is going to be your Y sequence, which is starting from now, going 120 time steps, and then we shift that one time step back. So the last value of your X is going to coincide with the first value of this right here. And then this is the Y value, so the fit function will take an X and then takes a Y, and then our Y is just our Y sequence. So let me run through this. And then this is pretty abstract, and it takes a little bit to get. And then there's a couple of blog posts that I think will be pretty helpful to go through. So I'll be including those in the deck. Oh my God. All right. So we should have used our CNN to try to do this, right? So like every time you see one of these, you're actually helping to train self-driving cars. So you're making a difference in the world.
Top right.
Top right.
Top left.
Top left. All right, there's a row there. All right, I think that's it, right?
We can do it by consensus.
All right. Oh man. All right. So all right. So what do I do about that top edge?
Yes.
I don't know. Who thinks I should click that?
What's the left of it? There's a little
Oh, it's right there. Oh, that's too little.
second from top left.
Second from top left?
That one.
Oh, that one. No. Oh.
Obviously, it thought there was one there. But everything on the page. There's a little bit. What's left?
So I guess like everyone agreed to like fuck with this. We can just like pick the ones that are not street signs, and then you just get a bunch of people killed, right? Adversarial attacks. All right, there we go.
We are not robots.
All right. So there's a 10-minute introduction to sequence learning. So it says 10 minutes, but it took me like at least a couple of hours to be able to translate this into our time series example. But yeah, I'll definitely include that link. Is it done training? All right, here we go. Okay, so we're not done yet. We're gonna build another thing here, and then And then remember that everything was modified in place, right? So then we can build another network using the building blocks of the previous network that we trained without actually doing any training, because the weights are already there. So this is for prediction. So our Keras model, so this is the functional API. You basically specify the inputs and the output. So we're going to take some encoder inputs and then output some encoder states. And then the decoder states inputs. All right, so these are just inputs that we're going to we're going to give something to these input layers, and then the results will be taking the decoder inputs. So this is analogous to what we were doing before, but I'll try to explain why we need to do this. And then we have the decoder stage. Recall that every LSTM output, the first thing in the list is the output, and then the second and the third one are going to be your hidden states. And then we have, we're going to pass the output to a dense layer. And so our model, the big picture is that we have this decoder model that's going to take some decoder inputs and some states, and it's going to produce some outputs, and these are the things that we care about, but then we also need to output the states to be passed on to the next time step. So this only makes sense if you look at all of this together. So similar to the one where we're iterating on the one prediction, we also need to loop through the time steps in this case. So let's see if we can wrap this up in 5 minutes. So this thing is going to take an input sequence. It's going to take an encoder model and a decoder model, and then we specify how many time steps we care about. So the first thing we do is we want to get some states by passing our input sequence to our encoder model. So our encoder model was defined, right? So it's not defined up there because it's an argument to our function, but we're going to pass to it our encoder model, which was defined up here, all right? So we take some input sequence, we're going to summarize it, and then we have a target sequence. So this is just some reshaping, and then this is basically taking the last value of our input sequence, and then that's going to be used to kick off our projection. So again, we have a forecasted sequence that we initialize that's empty right now. And then in each step of the iteration, what we do is we use this decoder model to, it's going to take this target sequence, which is the actual value, and then it's going to take some summary that came from the previous sequence. We're going to get an output value, and then that output value is going to be concatenated to our forecast sequence. And then now our target sequence is going to be updated by the output value that we just produced, and then we're going to update the states. And then at this point, we're sort of like moving one step into the future, and then we're using the outputs like we were doing before in our first example, but we are also passing the hidden states from the previous time step into the prediction. So once we've looped through 120 steps, we'll have some predictions. So did I not run this block? All right, and then we can plot this to see what we ended up with. All right, so we're at the end of our time. So as promised, I'll be I think most people got the link to the repo, and then I'll be adding some more references there, so you can definitely check out the details that we didn't have time to go through. And any last questions? All right, thank you all.